All right, we're going to move to section 12.3. We're going to skip section 12.2. It has to do with drawing various geometric figures with straight edge and compass. It's a really interesting section. I totally suggest that you guys read that, but it's hard to test, especially that we're not going to be in class. It's really hard to do, so we're just going to skip that section. And we're going to move on to section 12.3, which talks about similar triangles. Oh, I made a typo, so I am going to fix it right now. Two triangles are similar. I don't mean congruent, I mean similar. Two triangles are similar. If one can be enlarged or shrunk uniformly, no stretching, to be congruent with the other. We'll define this a little more precisely in a little bit, but let me kind of show you what I mean. Actually, explain the app I'm using right now is excellent for showing this. Here's a triangle. Now, if I want to make a similar triangle, well, I can make a copy of this. That's not what I want. This one, I can make a copy of that. And then I can either enlarge it, or I can shrink it. And notice that it's uniformly. I'm not lengthening any of the sides or stretching anything. Everything's happening like I'm just zooming in or out. So that is the idea of similar triangles. And it doesn't have to be in the same orientation. You can have similar triangles that are rotated. These guys are still similar, even though the rotation is different, doesn't matter. So that's the idea of similar triangles. So let's be a little more formal with what we're talking about here. So when I say two triangles are similar, we'll call them ABC and DEF. The symbol here, just the tilde without the equals, this means is similar to. So when there's a correspondence of vertices such that two things, corresponding angles are congruent, and it's not that corresponding sides are congruent, but the ratio between corresponding sides is the same for every pair of corresponding sides. Let me give you an example. So again, here's triangle ABC. I'll label these in a second. I just want to make a copy of this and make it a bit bigger. So here is A, B, C. Here's D, E, F. Well, you saw what happened. I was taking the first triangle and making it bigger, so these guys are similar. So you can see these angles are congruent. The angles didn't change when I made it bigger or smaller. But the side pairs, let me just put some fictitious lengths in here. Let's say this length was, I'll just make this up, 6. This length is 7. This length is 8. And over here, let's say this length is 12. This length would be 14. This length would be 16. And how did I know that? Well, if I have one corresponding pair of sides, I know the common ratio. So let me kind of show you. So if I look at the corresponding pair of sides AB and DE, well, the length of AB is 6. The length of DE is 12. So that ratio simplifies to a half. So you can think of this saying the lengths of the sides of the first triangle are half the length of the lengths of the second side. And you can see that this holds for all pairs of corresponding sides. AC over DF. Well, that is AC is 7, DF is 14, which is, of course, a half. And BC over EF is 8 over 16, which is a half. So if you need to check if two triangles are similar, you would check that the angles are congruent and all pairs of corresponding sides have the same ratio. But if you know two triangles are similar, then all you need is one pair of corresponding sides to work out the ratio. And if you have one side in one triangle, you can work out the other side in another. In fact, that's the next example we're going to do. So let's do a quick example just to see what's happening here. So suppose that triangle ABC is congruent, or sorry, not is congruent, is similar to triangle, let's call it X, Y, Z. So let me draw one. Okay, and I'm going to copy it and just make it a little bit bigger so I have something that looks quite similar. There's my triangle. Move that over, make it bigger, and give it a rotate. Why not? Okay. So let's say this is A, B, and C, which means this is X, Y, and Z. Okay, I'm going to give you some measurements, but not all of them. So let's say we know, let's say this one is, let's say 9. Let's say we know this one is 15. Let's say we know this one is 6. And let's say we know side YZ is, what does that look like? That looks like about, let's say 12. Let's find the lengths BC and X, Y. All right. So we're told that these guys are similar, which is great. That tells us that all pairs of corresponding sides are in the same ratio. So the correspondence is given in the name of the triangles. So we know that AB corresponds to XY, AC corresponds to XZ, and BC corresponds to YZ. So the name of our triangles gives us our correspondence. So let's go ahead. We know we have AC and we have its corresponding side XZ. So we can work out our common ratio. So let's go ahead and do that. So we know that the ratio AC over XZ, this will give us our common ratio, so that's 9 over 15, and we can simplify that if you like to be 3/5. So the side lengths of triangle ABC are 3/5 the length of the side lengths of triangle XYZ. Okay, that's great. We have those. Let's continue. So we know, oh, maybe I'll scroll back up. We know AB, we don't have the corresponding side XY, but we do have the common ratio or scale factor. Maybe I can say that this is called the scale factor. That common ratio is your scale factor. Okay, so we know that the common ratio between any two pairs of corresponding sides is 3/5 in this case. So AB over XY, well, we know AB is 6. We don't know the length of side XY, but we know that has to equal our common ratio. The ratio between any two sides has to be 3/5. Any two corresponding sides, I should say, has to be 3/5. So now we just solve this equation for XY. So let's cross multiply and solve. So we get that 6 times 5 is 30 equals 3 times XY. Divide both sides by 3. We get that 10 is the length of XY. So we can put that in our diagram. This length here is 10. And finally, we have the other side we need to find, which is YZ, but we have BC. Or sorry, we need to find BC, we have YZ. So YZ is 12. We don't have BC, but we know that BC over 12 has to be 3/5. Every ratio of corresponding sides in two similar triangles is 3/5. So we solve for BC. Again, cross multiply and solve. And we get that 5BC equals 36. We divide both sides by 5, and we get that BC is 7.2. So we can put that in our diagram up here. So our unknown side BC is 7.2. And that's great. So similar triangles, as long as you know that scale factor and you have one pair of corresponding sides, you can find the lengths of any other sides provided that you know one of them. The last thing I want to talk about for this lecture are similarity axioms. I'll do it in black. Similarity axioms. That's not what I wanted to do at all. Here we are. Similarity axioms. Now, I don't want to talk too long about this. I'll just kind of vaguely do a few drawings, and I'll refer you guys to 3 examples in your textbook because they are pretty good, so you can kind of see how they work and what's happening with them. But the similarity axioms, they're side, 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 angle, angle, well, angle, and I'll explain why I put that in brackets in a second, and side, angle, side. So basically what it's saying, so the first one, side, 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 says the following. If the ratio between each pair of corresponding sides is equal. And you might have to find the correspondence. It might not be given to you, so you might have to try a couple of times. So if you know that the ratio between each pair of corresponding sides is equal for all 3 pairs, you know the triangles are similar. So what do I mean by that? I'll just do a little bit of a drawing. Let's say I know the following thing. So here is my first triangle. Let me make a copy of this. And let's make it a little bigger. So let's say I know the following things. I know, call this A, B, C, D, E, F. Let's say I have no angle information, but I know that the ratio AB over DE is the same ratio as BC over EF. Like if I do that calculation, I get the same number in both cases. And it's the same as AC over DF. If I find that whatever ratio I do with the corresponding pairs of sides, I get the same number, that's enough to tell me that triangle ABC is similar to triangle DEF. And when it's similar, I get the angle information. Once I know it's similar, I know that the corresponding angles are equal. So I get the rest of the information. So now that I know it's similar. So that's how side, side, side works. And I'm going to refer you guys to example 12.22 in your textbook in chapter 12.3. Have a look at that. The next one is side, angle side. So if the ratio between let's say two pairs of corresponding sides are equal. So you don't know if all three are, but if you know what two are, and the included angle, so that's the one right between them. I'll draw a diagram in a second. If we know each of them are congruent with each other, then the triangles are similar. And again, let's draw a little diagram. So let's say we know the following thing. Give these vertices names. So I'll use the marking, rather than straight markings, I'll use like these tilde style markings to say these sides are in common ratio with each other. So what that means is that, say, AB over DE. Oh, let's do it the other way around. It doesn't matter what triangle goes on top and what triangle goes on the bottom, as long as you're consistent. So let's put the other triangle on top, just for fun. So DE over AB, if that's the same as EF over BC, so if this is the case, and we know that angle B is congruent to angle E, if we know that, that's enough to tell us that the triangles are similar. Triangle ABC is similar to triangle DEF. So that's how the side angle side congruence works. And finally, Oh, I better tell you what example to look at in the book. Have a look at example 12.25. And then finally, we have angle, angle. Really, you can think of it as angle, angle, angle. Because if you know two angles of a triangle, you automatically know the third because you know that the angles of a triangle add up to 180 degrees. So, what this is saying, if corresponding vertices or angles are congruent, then the triangles are similar. So what is this saying? Let's do a quick picture to show this. So again, let me draw a triangle, and we'll copy it, and we'll make it bigger. And we can even rotate it. Let's rotate it. So let's say I know the following things. Let me give these some names. This is vertex A, B, C as usual. This will be D, E, F. So let's say I know that angle A here is congruent to angle D. Angle B is congruent to angle E. And angle C is congruent to angle F. Let's say I have that information. Then the angle, angle, angle axiom tells you that since you have that angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F, then by the angle, angle, angle postulate, or sorry, not postulate, axiom, you know that these triangles are similar. So triangle ABC is similar to triangle DEF. And remember, these axioms aren't things we can prove, at least not with the tools that we have. We just take them as rules of the game of algebra. So that's what's happening with these three axioms. Next lecture, we'll do a few examples to show how these axioms can be useful. Especially, we're going to use the side angle side axiom quite a bit. We're going to come up with some ways of drawing similar triangles, which is really cool.